This is video 83 in our series on tensor calculus. In this video, we'll introduce the concept of Riemann normal coordinates. Now, we'll first define what they are, and then we'll demonstrate that one of the properties of a manifold, as we've defined it, is that you can always transform to Riemann normal coordinates. In future videos, we'll use Riemann normal coordinates as a convenient tool for analyzing the properties of the Riemann tensor. Tensor calculus works for any coordinate system, but there is a class of coordinates known as Riemann normal coordinates that often simplifies the analysis we're trying to do. So let's define what we mean by Riemann normal coordinates. They're defined by two properties. The first is this, that the metric tensor S alpha alpha, when evaluated at a point of origin P sub 0, is equal to 1 when the two indexes are equal and 0 when the indexes are unequal. The second property is this, that the partial derivative of our metric tensor with respect to the coordinate is equal to 0 if evaluated at point P0. Now you'll recognize these properties as the general properties of a Cartesian coordinate system. But in that case, these properties exist everywhere in the manifold. They're constant throughout. What we're saying here is that Riemann normal coordinates are not Cartesian coordinates, but they look like Cartesian coordinates if we look at them specifically at the point of origin P sub 0. If we move away from this point of origin, these properties no longer exist. All right, well, an immediate consequence of this definition is found by remembering the definition for our Christoffel symbols. Now, the Christoffel symbols are defined in terms of the partial derivatives of the metric tensor. So if all of these are 0 at point P sub 0, then it follows immediately as a corollary here that the Christoffel symbols evaluated at the same point of origin, that is, when we look at this particular point, the Christoffel symbols will be equal to 0. Again, they're not 0 everywhere in the manifold, but when we evaluate them at this point, the values are equal to 0. Okay, the best way to understand is with an illustration. So let's illustrate this concept using our spherical surface. Using the spherical surface as our manifold, we're going to define a set of coordinates this way. Now, the S alpha coordinates are theta and phi, which are our standard coordinates. Theta, of course, is the angle from the pole down this way, and phi is the angle moving from here around in the circle, this little gate that we talk about. So we're defining two new coordinates, u and v, in terms of theta and phi, and we define them this way. So here's the transformation from S to S prime, and this is from S prime to S. Okay, what we want to do then is to find the metric tensor for our new coordinate systems right here. Well, to do that, we fall back on our transformation rule for the metric tensor. This metric tensor in the prime system equals that in the unprimed system times these Jacobian factors. That's just our transformation rule where we have one Jacobian factor for each of our free indexes. Okay, well, the metric tensor S alpha alpha is something we discovered back in video number 61, and that's this. So relative to coordinates theta and phi, this is the metric tensor in our standard coordinates for a spherical surface. So if we want the metric tensor here, we have to perform this transformation, and that means we need to derive these Jacobian factors. Okay, so it works like this. We have Jacobian factors J alpha, alpha prime will be equal to all the possible partial derivatives of our S coordinates with respect to our S prime coordinates. So we work our way through it. The partial derivative of theta with respect to u is simply equal to 1 over a. Pi over 2 is a constant, and when we take the derivative of this term, we just get 1 over a. The partial derivative of theta with respect to phi is equal to 0 because it doesn't depend on phi in any way, so this is 0. Now the partial of phi with respect to u is 0. It's not dependent on u at all. and the partial of phi with respect to v is 1 over a. So that gives us the set of Jacobian factors we need for this expression. So what we need to do is to apply these values here and here back into this formula. All right, let's start with S1 prime 1 prime, and that's going to be equal to this whole side expanded out, but we only need to consider the S alpha beta terms 1, 1 and 2, 2. These cross elements here are 0, so we only need 2 terms on the right-hand side. So we'll have S11 times J1, 1 prime, J1, 1 prime, plus S22 times J2, 1 prime, J2, 1 prime. Again, we can skip S12 and S21 because there's 0 right here. All right, let's plug in the actual values. S1 prime 1 prime will equal a squared times J1 1 prime. There are 2 of them, so it's this value squared, which is 1 over a squared. And then the second term, S22, is a squared sine squared theta, but J2 1 prime is equal to 0 here. So this whole thing evaluates out to simply the value of 1. A squared times 1 over a squared, and this term is equal to 0. So our first term over here, S alpha prime beta prime, we'll build up this little matrix here. Our first element is simply equal to 1. All right, let's try S1 prime 2 prime, and that's going to be equal again to this time with Jacobian 1 1 prime, Jacobian 1 2 prime. These 2 indexes down here have to match these indexes each time. So S22 times J2 1 prime, J2 2 prime. Well, this guy is equal to 0, and this guy is equal to 0, which means the whole thing is equal to 0. That means that we can put a 0 right over here. All right, looking closely at this expression, if we flip these indexes, then we would simply wind up flipping the order of these 2 terms right here. So the same result applies in our second row, first column, right down here. Of course, we already know that these off-diagonal elements are going to be equal because this is a symmetric relationship. Okay, so finally, the last one will be S2 prime 2 prime, S11 times Jacobian 1 2 prime, Jacobian 1 2 prime, plus S22, J2 2 prime, J2 2 prime. Well, these guys are equal to 0, so we only have this one term. Therefore, S2 prime 2 prime is equal to this element, which is a squared sine squared theta, times J2 2 prime squared, that's this guy up here squared, 1 over a squared is just equal to sine squared theta. And that gives us the result for this term right down here. All right, that then is our metric tensor expressed for S alpha prime beta prime. Now this result is correct, but what we'd like to do is to express this result in terms of our coordinates u and v. So to do that, we note that sine of theta can be expressed in terms of these other coordinates by using this expression up here. So we'll apply the trig identity for the sum of 2 angles. This would be equal to the sine of u over a times the cosine pi over 2 plus the cosine of u over a times the sine of pi over 2. Well, cosine of pi over 2 is equal to 0. The sine of pi over 2 is 1. So this whole thing evaluates to this term right here by itself, cosine u over a. So with that, we can go back over and simply delete this value right over here. And in its place, we will put the cosine u over a squared. And that's the result we're looking for in terms of the coordinate systems, that the coordinates that match the indexes alpha prime and beta prime. Next, let's find all of the partial derivatives of this metric tensor with respect to our coordinates. Well, 3 of these are constants, so those partials are all equal to 0. The only partial that's not equal to 0 is the partial of this element with respect to u. So we can say that the partial derivative of S2 prime 2 prime with respect to S1 prime is simply the partial of this with respect to u. Well, that's a negative 2 over a times the sine u over a times the cosine of u over a. So this is the only non-zero partial derivative of our metric tensor over here. Having derived these results here and here, let's now evaluate them relative to the origin. Well, what's the origin? P sub 0 here is simply the place where u and v are both equal to 0. So if we set u equal to 0, then this term becomes 1. The cosine of 0 is 1. The sine of 0 is 0, so this whole expression is equal to 0. So what that tells us is that at the point of origin right here, the metric tensor is just the identity matrix. It's 1, 0, 0, 1. And this partial derivative is 0 along with all of the others because of the constants. So this set of coordinates, u and v, as we've defined them here, qualify as Riemann normal coordinates. Well, having seen the analytics, let's spend a couple of minutes talking about this from a geometric perspective. First of all, our point of origin. When we say the point of origin is located where u and v are both equal to 0, where is that on our surface? Well, when u is equal to 0, theta is equal to pi over 2. When v is equal to 0, then phi is equal to 0. So we're talking about this point right over here, where theta equals pi over 2 and phi equals 0. What's so special about this point? Well, it happens to be the point where we have the intersection of these two arcs. And these two arcs are both great circles. Well, what is a great circle? A great circle is simply the circle on the sphere that is generated when we pass a plane through the center of our sphere. So if we pass a couple of planes through the sphere like this, one vertical and one horizontal, with the intersection will be these two great circles that intersect at our point of origin right there. Well, another way of saying it is that each of these planes is defined relative to the normal. Each plane, this one and this one, contain our normal here. So using the normal, we construct a plane, one that's vertical, one that's horizontal, and the two of them cut through the surface, generating these arcs, which become the coordinate lines for our new coordinate system, u and v. Well, there's nothing special or unique about this particular point. We could do the same thing at any point on the sphere. For example, out here we could create a normal. We could construct planes that use the normal and intersect with each other at right angles, and the intersections of those two planes with the surface would generate two great circles, one this way, and we'd be able to construct a Riemann normal coordinate system relative to this point. So the other thing to note here is that this process is not unique to the surface of a sphere. The same process can be used on any surface where we simply find a point, construct the normal, construct two planes that intersect at right angles with each other, and use the normal as that line of intersection. And then the arcs that they generate as they intersect the surface will be the coordinate lines for a Riemann normal coordinate system. The other requirement is, of course, that the scaling factor of each of those coordinate lines needs to be simply the arc length of the line, so that the scaling factor is 1, and that guarantees us that these factors will be 1 down here. So that process of constructing these two planes and intersecting using the normal is something that can be done at any point on any surface. And because they use the normal in this way, that gives you some insight as to why we call them Riemann normal coordinate systems, because they use the normal in that construction process. Another point to be made here is that the rotational orientation of these planes around the normal is quite arbitrary. We've got the freedom to rotate these planes right or left any way we want to, as long as the two planes remain perpendicular to each other. Well, if this whole process seems familiar, it should. This is exactly what we were doing back in video number 78 when we talked about Riemann curvature. You might go back and watch that video again in light of what you've learned here. Now, one of the important properties of a Riemann manifold is that we're able to construct a Riemann normal coordinate system at any point on the manifold. This is true not only for any surface, but it's true if we're working with higher dimensions as well. So I want to spend a few minutes showing you how we know that's true. We'll start with our transformation equation to the S' system, and we'll take the partial derivative of this with respect to S omega prime. So we'll have the partial of S alpha prime beta prime with respect to S omega prime. Well, on the right-hand side, we of course have to apply the product rule. So we'll first take the partial derivative of this term. So that's the partial of S alpha beta with respect to omega prime, but I'll really take the partial with respect to S omega and add a Jacobian factor of J omega omega prime. So this is really just an application of the chain rule to this term, because we want to express this partial derivative in terms of the unprimed system here. We've done this several times before. Okay, we need to follow through with the rest of the terms here. We have J alpha alpha prime, we have J beta beta prime, and then we have to follow through with additional terms to complete the product rule. So S alpha beta times the Jacobian alpha alpha prime omega prime and J beta beta prime, and then same thing for this last term. So it's plus S alpha beta, this time it's J alpha alpha prime, and we take the second partial derivative out here, beta beta prime omega prime. Now, if we're going to wind up with Riemann normal coordinates, there are some restrictions on the outcome here. This term up here is going to be equal either to 1 or to 0, depending on whether the indexes are equal or different. And this expression has got to be equal to 0 in each case. So what we have is a set of equations, relationships, that have to be met in order for us to get the Riemann normal coordinates. Well, how many equations do we have here? Let's look at it a moment. Here we've got 2 free indexes, so there are 4 different relationships here because of the 2 indexes. Down here we've got 3 indexes, so we have a total of 8 expressions here. So at first blush it looks like we have 12 equations here that have to be satisfied to meet all of these conditions. But that's not really true, because these equations are not independent. For example, S1 prime 2 prime is equal to S2 prime 1 prime. So although there are 4 equations, 2 of them are effectively the same condition. We have the same thing going on down here. We've got what looks like 8 expressions, but 2 of them are identical because we can flip-flop these 2 indexes. So in reality, what we have here is a total of 3 independent equations here. We're eliminating this duplication, and then we've got a total of 6 here because we're eliminating the 2 duplicates here. So in the end, what we have is a total of 9 conditions that have to be met, 9 different equations that have to be satisfied. Well, if we've got 9 different conditions or equations that have to be satisfied, we're going to need at least 9 independent variables to be able to have the freedom to satisfy all 9 of these conditions. Well, what are our free variables over here? Well, they're these Jacobian factors. So how many of those do we have? Well, there are 4 different Jacobian factors, and then we also have the second partials down here, these guys. So how many of those are there? Well, we've got 3 indexes, so it looks like we have a total of 8. But again, we have some duplication because things like Jacobian 1, 1 prime, 2 prime is the same as J 1, 2 prime, 1 prime. Remember, these are partial derivatives of one coordinate with respect to another, and these indexes here represent the second partials, and the order of the partials doesn't matter. So although there are 8 different factors here, there are only 6 independent factors because 2 of them are duplicates here. And that means that we have a total of 10 different independent variables when we count all the Jacobian factors and the independent second order factors here. Well, that works out just fine because we have one more independent variable than conditions. We have one additional degree of freedom. And so you know that when we have 9 equations and 9 variables, we're going to have one unique solution. When we have more variables than conditions, we say that the situation is underdetermined. That simply means that we can find a whole set of solutions here. We have one degree of freedom left over, and this extra degree of freedom is what gives us the ability to rotate the axes in the process of finding these Riemann normal coordinates. But we have enough freedom to establish Riemann normal coordinates on any surface. Now, using similar logic, we can actually work out these numbers in a general fashion for any number of dimensions. I don't have time to work that out for you here, but I'll give you the final results. This formula would give you the number of conditions that are represented by the various equations. So it's 1/2 of n times n plus 1 squared. And then this expression would give you the number of degrees of freedom that we have for any dimension of n. And then this number is always larger than this one, and we can work out the difference in the number of degrees of freedom to be equal to this. So you can plug the numbers in here yourself and see that for 2 dimensions, this turns out to be 9, this is 10, and this is 1, as we found just a moment ago. And then for 3 dimensions, we'd have 24 conditions, 27 degrees of freedom, and 3 extra degrees of freedom here. Interestingly enough, this is just the number of degrees of freedom we need to rotate a 3-dimensional coordinate system in any of the 3 axes. So with that, you can clearly see that it's always possible to establish Riemann normal coordinates, no matter how many dimensions we're working with. Now, it may have occurred to you whether or not we can extend this to the second partial derivatives, and the answer is no. If we were to extend this analysis and take the second partial derivative of our metric tensor elements, we'd find that we're going to wind up with more conditions than free variables over here. In that case, our conditions are going to be overdetermined. We have more equations than variables, and that makes it impossible to find a solution. So it only works for the first order. We can always transform away the first partial derivatives, but nothing more. Well, all of that is well and good, but what does it have to do with the Riemann tensor? Well, we'll move on to address that point as we bring the video to a close. We ended the last video with this general expression for the Riemann tensor using only lower indexes. Well, given that we can find Riemann normal coordinates anywhere in our manifold, what happens if we transform this equation to those coordinates? Well, the main feature of those coordinates is that all of the Christoffel symbols evaluate to 0 at the point of evaluation. So that means that this expression simplifies to the fact that all of these terms drop out. They all become 0. And that greatly simplifies the complexity of this expression. So now we have only two terms to work with, and we can continue to simplify the expression by expanding these two terms out. Well, we do that by reminding ourselves of the definition of these Christoffel symbols of the first kind. It's given right here. So we'll simply apply this pattern to each of these terms in turn. So we'll apply it to this one first. For the second term, all we've got to do is to switch the indexes alpha and beta. Now to complete the expression, we're going to add this term and we're going to subtract this term as per the expression up here. Now in the process, notice that this term and this term will cancel out. They're identical. Remember that the order of differentiation doesn't matter. So the final result is going to be left with 4 individual terms here. Now this final form will prove to be very useful and convenient when it comes to evaluating the various symmetries and identities of the Riemann tensor. And that's exactly what we're going to do in the next video.